Number 4 is very similar to what we did in class today, actually.
Huh? What?
Right.
Hey, Mr. Seaweed. I know. Yeah.
You know what?
I did that.
Okay, in class today.
Oh no, the clipboard's in front of the wall. That's staying there for a while. Yeah.
Hey, can we focus some? I don't want to stay here like all day. Are you leaving? Okay. See you. So in class today, I tried drawing this picture for you, and I completely screwed it up. I just told you to memorize what I was trying to get at. So let me redraw it, because I think this, if you see this, it's going to help you remember the relationship. I made a pretty drawing here. So if we have some object on an incline, right, which is a very common physics problem, some object on an incline, we know that the force of gravity is going to pull this object straight down, right? And in every incline problem, you're going to have to deal with the force of gravity. Right? The problem is the angle that's being given to you is weird when you're looking at the object on the incline. So this is how the trig functions end up being. So,
Well, I was given 30.
what's up? Yeah, I know. I put theta in. I don't know. I'm just showing you where this relationship comes from. This is the start of number 4. So we know that there's going to be 2 things that the force of gravity does. One thing it's going to do is it's going to pull our object in which direction? Down the ramp. It's also going to pull our object
Up.
not up.
Oh, yeah.
Gravity, really?
Opposite. Wait.
Where? Okay, it's going to make it slide, but it's also going to pull it into the ramp. Okay. It's going to pull it into the ramp, and it's going to make it slide down the ramp. Those are the 2 things it's going to do. So in this drawing, the part of the force that's going to make it go into the ramp is actually the result of the normal force, right? Because it's perpendicular to the surface. So this line right here, I'm going to try to draw it as pretty as I possibly can. This line right here, okay, would be the number 2, right, into the ramp. This line right here, let me do a different color. This line right here would be the line that makes it slide down the ramp. Okay, what did I make here? Right triangle. Okay. Without going into the algebra, I'm just going to tell you, this angle is also theta. It's the same measurement.
Is it always going to be?
Yes. All right.
Wow.
It's the same measurement. Okay, so here's where that little thing I told you in class comes from. If I'm looking at this angle theta, right? Okay. Wait, did I label the right angle correctly? No. My picture is off. This should be the right angle. Let me fix that. Because if that's not
Then that
I know.
makes sense.
if that's not right, then we have a problem. Okay. Oh, erased it.
Wait, can they hear us?
Yeah.
Oh,
All right, I'm just gonna start over because this. Sorry. Okay, angle theta. Got some object up here.
You know how to do. Yeah, I know. That's what I'm thinking. How?
Okay, there's the force of gravity. Our other one is going to be, and I didn't draw this right first time. It's going to be perpendicular to the surface. That looks like. No.
I think you're doing your gravity.
No, it's.
That's the same way you just did it.
Yeah, but that's exactly.
No, this is right. I want this to be the right angle. This is the problem. I'm drawing this too long.
We want
Right here. So let me do this. I'll cheat a little bit. No, not erase.
Oh, make another triangle.
Okay, so this would be the part that slides down. No. What am I doing?
The right angle is the one on the right.
Yeah.
So
Sorry.
The fourth, like actually.
I drew this perfectly in one try. When I did it on a little note thing.
How do you know?
Well, that's what I'm trying to do, but apparently my brain is like farting instead of working.
Make it also slide down, like flip it.
Yeah, this is how it's supposed to look. It's not going to look perfect, but okay. So this would be the part that makes it slide down. Pretend this is a right angle. It's close enough. Right? This is still theta, right? Those two angles are equal. So if I want to split the force of gravity right here into its two components, what would this be? Fg what? Look at where your angle is. It's adjacent. It's adjacent here. Fg cosine theta would go here. Fg sine theta would go here.
Okay, so we're matching it.
Okay. Yeah, my point is, when you're dealing with an incline, what we memorize for vectors doesn't work anymore. X and y, like cosine with x, sine with y, doesn't work on inclines. This is why. It's because the angle you're measuring is weird. Okay, so the actual, what you would think is the y component, the one that's going into the ramp, is cosine. Right? The one that's going down the ramp, what you would think is x, is sine. So the little thing I gave my class today is cosine cores, meaning it buries into the ramp, and then sine slides, meaning it obviously just slides down the ramp. Right? If you memorize this, you'll be fine, as long as the angle you're being given is this one. Sometimes they'll trip you up and give you the angle measurement up here. If they do that, then it's just cosine is x, sine is y, I believe. And I'll double check on that, but I think it's just the same as we're used to doing. So, knowing this, cosine cores slides, sine slides, number 4 is a very easy problem. They're going to give you, it's just a car on a ramp, some angle theta. Alright, they give you, the mass of the car is, mine's 1,200 kilograms. They give you the angle, and mine is 30 degrees. They tell you that g in this problem is 10 meters per second squared, which you'll see sometimes. Okay, and it asks, what is the force of friction if the car is being what? It's parked. Okay, so it's stationary. What can we say about what's zero? Net force. Acceleration is 0, which also means that your net force has to be 0. So if you're looking at a free body diagram of your car on the ramp, in order for the net force to be 0, then the slide, the force of the slide has to equal the force of what? The force of the friction, right, holding it up the ramp. So those two things have to equal each other, right? Yeah. So really, what you can solve for either one. You could solve for the sliding force, and you could solve for the force of friction. In this one, it's probably, since we're saying the force of friction is going to hold the thing up, let's solve for the force of friction. We know that frictional forces are equal to mg mu, where mu is the coefficient of friction, which has to be given to you in a problem if you need it. Right? They're never going to trick you with that. You can't derive that from anything. In this problem, we don't need it though, right? Because we just need to solve for the force. We know in this problem, cosine cores sine slides, so the frictional force has to be equal to, it's going to be equal to mg, right? The net force, or the force resulting from gravity, mg times sine theta. That's how I wrote the first one. Yeah, it's the force of gravity. But yeah, since we know m and we know g, that's how I'm going to write it out.
So your mass is going to be 12.
So this is a very simple problem. All you do is plug in from this point. Like, and for most of our incline problems, this is going to be the first step, is finding out the force pulling the thing down the ramp and finding out the force that's pulling it into the ramp.
What is M? Math? M is math, right?
Yeah, math.
So cosine is the vertical one, and sine is the horizontal.
Right. Cosine cores, sine slides. Yeah, you just plug in whatever your numbers are here. Easy, right?
6,000.
Yes!
It should be.
What did you get?
No, I'm number 9.
No, we use kilograms. Kilograms are a standard unit for mass. No, yeah, 10 might be throwing you off.
That one, you got 6,000. Look, his numbers